So I've got 1:30, right? 1 hour 30 minutes, right? Yeah. Okay. Good morning. I hope you've woken up because this is going to be very exciting. So I was supposed to tell you about heat flow, but in fact I'm going to tell you mostly about heat production because I think that's a variable that's seldom taken into consideration at the right level. So all this work has been done with my colleague Jean-Claude Maréchal from University of Quebec at Montreal. For those of you who were watching American TV in the 60s or 70s, we are just very much like the odd couple. So I didn't put this on the wiki, but we just published a book on this, Cambridge University Press. So I've brought a copy here for the CIDO students. It's one of those competitions where the first prize gets one book, second prize gets 2 books, etc. So, but it's here. So this is a better heat flow map than the one that's been shown previously, because it shows clearly that most of the Earth's heat loss is achieved through the oceans. And you can see on that color scale that the continents are quite barren. But in fact, that's only a result of the color scheme, which focuses, of course, on the high heat flow areas. The continents have got a lot of details in them. And this is what this talk is going to be. So measuring surface heat flow, in fact, can tell you a lot. It's a variable that tells you about what the rate at which heat is flowing out of the Earth. So it can tell you a lot about the crust, because some of this heat is heat that's produced by the decay of uranium, thorium, and potassium in crustal rocks. So the interesting thing is that it gives you an absolute value, an integral of all the heat production. So it tells you about the whole crustal composition at one go, including the lower crust, which is seldom available for sampling at the Earth's surface. It also tells you about the lithospheric structure, how deep it is, how deep must we go to reach a mantle isentrope. And also it tells you when you invert for the data, you can get the basal heat flux, because we can demonstrate that heat is actually being brought up to the lithosphere from below, and that's a strong constraint on what goes on in the mantle, and in particular on rheology, because the mantle has got to be able to be sufficiently vigorous to sustain this heat flux. So you can see that it provides a lot of constraints. So the plan is, for those of you who don't know what heat flow is all about, shame on you. So I'll just say a few basics about measuring heat flow. Then what do we need to be able to calculate temperatures? Then how can we determine crustal heat production? That's Roberto has been giving us average models for the crust, but of course there's no such thing as one particular location where you see the average crust. From when you go from one place to another, you're going to change, the crustal structure changes. So how can we look at the local heat production? So how we can determine the bulk value, and how can we get a handle on the way it's segregated between the upper crust and the lower crust. And that's, as I will show you, that's a very important issue. And in fact, it tells us a lot about also petrological processes. The Earth's crust differentiates and puts all the radioactive elements at the top. And there's a very, very good reason for this. I'm going to show you that a crust that is not differentiated is not stable thermally. Then we are going to see whether all this is a figment of our imagination. We'll be trying to check the temperatures that we calculate, and I will show you the way we've done that. And then we're going to go into large-scale systematics to show what can we do, a general statement that is valid. I'm afraid I'm going to tell you there's not such thing. So you have to account for the local structure, the local geology. And some systematics of crustal heat production that tells us, I think, quite a lot about what goes on in the crust. And finally, remind us that the way the crust behaves has an important influence, and is influenced by mantle convection. So all this is, in fact, part and parcel of the same problem. So how do you determine continental heat flow? We begin with Fourier's law of heat conduction. Heat flux is lambda, this is thermal conductivity times the gradient of temperature. Lambda is something that you can't estimate from other physical properties because it's sensitive to sometimes minute concentration of minerals. Quartz has a huge influence on lambda, for example. And so in practice, when you measure it in the field, because the Earth's surface is an isotherm, roughly, then the heat flux has got to be vertical. It's got to be perpendicular to that isotherm. And so you measure the vertical temperature gradient. The world average is 80 milliwatts per square meter, just about, and the continental is much lower than that, and the cratons are even lower than that. So just to show you what kind of data that we can get, this is some of the data that we've been collecting in the Canadian Shield as temperature as a function of depth. Look at the scale. To make reliable heat flow measurements, you need to do measurements over a large depth range, because you need to check that no heat is lost between the bottom of your hole and the top of the hole. There might be lateral heat transfer, in which case you're missing it, and what we're interested in, the rate at which the Earth is losing heat, vertically. So you can see you got very nice profiles down to several kilometers if you can. With our equipment, you can go to 2.3 kilometers, not much more, for reasons that I will show later. The gradients for these balls in the Canadian Shield, I've chosen them to be on the low side, about 10 Kelvin per kilometer. You're in the Craton. Sept-Îles is in the Grenville province, and Beaumont is right in the Superior province, about 10 on average. These are some of the lowest heat flow. So what do you do to measure heat flow? First, you carry the stuff, and you go through horrible swamps, etc., flies, black flies, etc. But it's exciting, and there's raw passion that goes into this, okay? And then you measure it, and logging a hole is also exciting because it takes a couple of days. So you sit and you watch. Sometimes there's a squirrel coming by, or you just get in a fight with the other half of the odd couple. Okay? And then you got to retrieve the samples, and that's it's one of the needle in the haystack. So Canadians like to drill holes. I don't know why. And so what you have is somewhere in these big piles, you have sometimes up to several hundred miles of cores, and you've got to find the cores for your particular hole. And so it takes also quite a bit of time. That's me here. So this is why it's not very productive. You can't publish lots of heat flow papers. It takes time. One heat flow measurement takes you about a month on average. You got to locate the hole, you got to go there, you got to measure it, then you got to get the samples, measure thermal conductivity. So this is why this is a field where there's not many practitioners. In fact, it's very hard to get funding for this. So I fund all of this work through what's leftovers from other grants. One advantage is that the heat flow community is small, so if you want to hold a heat flow workshop, you can hold it in a telephone booth. It's easy. The other advantage is that you can meet nice things. So this is an Arctic fox, and so we measured holes just in the Raglan mine, which is up Hudson Strait, and this little guy was very curious about us. He obviously wanted to know more about heat flow. So that's the heat flow map for continents. Now we've changed the scale. We don't have the oceans to mess up our image. And you can start to see there is a lot of structure in the heat flow field of continents. Of course, the western of the United States is an active area, so there's lots of high heat flow values. But even the shield itself, which looks like this big blue patch, in fact, some of this is because there's no heat flow measurements, has got some structure to it. So although you might think that Archean or Proterozoic cratons are barren things in terms of heat flow, it's not true. And in fact, there's quite a lot of local variability. And this was not appreciated, say, 30 years ago. So most of the scientists, everybody uses temperature, everybody uses geotherms, but they were all based on early work in the 70s, which were rely on a very meager data sets. For example, in the Canadian Shield in 1980, when we started doing this work, there was about 25 measurements in the Canadian Shield, maybe up to 30 if you include bad measurements. So, and now we've added about 250 of them. Yes?
So these are based on borehole measurements?
These are all based on borehole measurements, yes.
What's the coverage?
I'll show you the coverage later, yeah. On this map, there would be too many dots. The number of continental heat flow measurements worldwide is about 1,000, something like that. In the oceans, it's about 10,000. The ocean is much easier. First, you just stick a probe in the sediments, and besides, you got all the ship that does this for you. You don't have to carry the cable. You don't have to do all this nasty work. And so it's much easier. Yes? No, in Antarctica, there's a few measurements you can see along the coast. There's, in fact, I counted, there must be 5 or 6 measurements all along the coast.
So the pattern, the heat flow pattern for Antarctica, is derived from some kind of
No, it's derived from just continuation of extrapolation between data points. So you can see there's not a lot of structure there. I'll show you when I'm zeroing in specific areas. You'll see the data points. That's for North America. You can see again that now we can see some structure. Again, the shield here is again all blue. Most of the action in terms of heat flow seems to be there, but I will show you there's a lot of action there too. You can see there's start appearing patches like that, and that's a map of the mostly the eastern part of the Canadian Shield. That we've got the Appalachians, the Granville, the Superior Province. We're going to the Trans-Hudson orogeny here, which is Proterozoic, and then you go into the Slave and other cratons. And these are the dots. Most of these measurements are ours. These windows are windows that I will mention later on. These are windows where you can produce local averages of heat flow and heat production to look at systematic studies, and I'll go back to in a minute why we're doing this. But you can see the measurements. There's a lot of measurements that were done using sea flow measuring techniques in the Superior Province, in the Lake Superior, and hence this very dense array of points here. You can see the coverage is far from complete, but we've been able, in fact, since this map was produced, we've been able to add measurements in the northerly parts of the shield. The red dots are the new measurements that were done in the paper that we published.
Can you say a little bit about the error bars on these measurements and what the sources of error are?
Okay, so let's go back. The error bars is essentially you can calculate. There's two things that can enter. You want to make sure that there's no heat that's being lost in between here and there. So we calculate the standard deviation of measurements that heat flow measurements can produce. You can determine here, there, etc. So all along the profile. So we have the standard deviation of the heat flow all around the profile. That's one area of there's local variability that you can account for. The shallow part is affected by recent climatic changes. In fact, we use that to invert for ground temperatures as a function of time, which tells us something about climate. So you can't use the shallow part of the borehole because it's solely determined by the climatic effect, and then the background signal, which is the heat that's been leaving the Earth, is too small for comfort. It's overwhelmed by the climatic signal. You can see that climatic signal completely overturns the profile. The errors are basically local variability in the rock type. And the main concern is that you might have heat refraction, because sometimes you have a conductive body next door which will going to suck up some of the heat. So the way we do this is we try to measure a couple of boreholes to make sure that they are identical. So basically, in the end, thermal conductivity by itself is measured to a precision of about 3%. It's a transient thermal property. It's very hard to go below that, so 3% just for thermal conductivity. Local variability in the gradient, etc., which is probably due to varying rock type that's on the scale that you can't sample easily. So overall, I think heat flow measurement is probably not better than about 6-7%. But in the Canadian Shield, what we've done is we've logged these very deep boreholes, so the climatic signal, we determine it perfectly because these very deep boreholes allow us to determine it. So it's not something that we assume. We have the climatic signal down pat for all the sites that we have. Does that... So to go back on what we need to make sense of this data, so we need to say something about the crust. And I'll refer to the Moho heat flow, which is the heat flow at the Moho, which might not be exactly equal to the heat flow that's supplied to the base of the lithosphere, because that might be some amounts of heat-producing elements in the lithosphere. I will not talk about this today, and I will assume for all practical purposes that it is zero, because most I'm going to show you are crustal profiles. I will show you some lithospheric profiles, but for the moment, let's not worry about this. So to make sense of the heat flow data, we must account for what's produced in the crust. And we must estimate the heat flux at the Moho. So some requirements, then you need to know the distribution of radiogenic heat production. Then you can calculate, in principle, you have to account for the temperature variation of thermal conductivity, which is significant. It varies by more than a factor of 2 over the temperature range that we're interested in. Then you need, of course, to know the crustal thickness, and I will show you later how we can correlate temperatures with PN velocities, and I will show you why we've chosen that. So the parameters that we can measure easily are the crustal thickness, which is provided by seismology. Thermal conductivity as a function of temperature is known. We can measure the surface heat production. We can measure the surface heat flux, and what is not known directly is the Moho heat flux, and we spent quite a bit of time to get at this number. We can use, I will show you some of the data, Xenolith data that tell us about temperature gradients in the lithospheric mantle below the crust, and that will tell us the heat that's flowing through that part of the lithosphere, and hence it will provide you an estimate with the Moho heat flux. But we can also sort it out using heat flow systematics, and I will not talk about this today. There are some things we can do. Basically, the crustal signal is a short wavelength signal, and this wavelength over which this varies is a much larger wavelength, so we can separate. It's the usual trick in geophysics. You separate short and large wavelengths, and that's what you can do. So what I want to show you is that with what we've got, which is not much, if we know HC, we can, if we can determine the Moho heat flux, then we can say a lot of things about the crustal heat production and the way it's distributed with respect to depth. So I will show you how we can do this. And so the main unknown is the mantle or Moho heat flux here. How can we go about it? I'll show later on how we do this. So if you have all this information, then once D steady heat equation, I'll show you why it's 1D steady state, because we have to work on a certain scale to make reliable calculations. So you integrate this equation straightforward. And you need, of course, to account for the distribution of radioactive elements over the crust. So you measure this, you measure surface heat production. This is known, and we must say some things about Moho heat flux and the way crustal heat production is distributed with depth. So the main issue is that the crust is extremely heterogeneous. That's a very accurate representation of what the crust looks like. But of course, if you measure heat flow here, say this is a very radiogenic plutons, and some of the early measurements, for example, in the Appalachians done by Francis Birch and his colleagues, zeroed in on some of the most radiogenic plutons in the world, the White Mountains magma series. So they get whopping signals over these plutons. But of course, what you record is mostly the heat that's produced within the pluton. It's very hard to extract from that the background heat flux, which is not affected by this. So it's well known that it's a downward, what we call in geophysics, downward continuation. If you've got small wavelengths at the surface and you leave them, then as you go deeper, then these wavelengths, I will show you in a minute, blow up, and so your signal becomes completely unstable, and you end up with infinite heat flow variations at sufficiently large depths. So you must average out your structure, because you don't want to have one heat flow measurement which is completely biased by an anomalous pluton or rock type. So this is why we've got to measure a sufficient number of sites to make sure that we get a good reasonable average value that is not affected by some local things. So the trick is, that's from potential theory. If you're measuring heat flow at this point here, you're going to average crustal heat production over a lateral scale that depends on the depth. And the rule of thumb is that the lateral distance over which you're averaging your heat production goes as 2 pi times z, the depth at which you're considering heat production. So you can see you've got this cone, and the deeper you go, and the larger the averaging that has been made. So if you convert numbers, that's something which is important. If you look at a crustal thickness of 35 kilometers, then a heat flow measurement here tells you something about the average heat production over a scale of about 220 kilometers at the base of the crust. So this need not, if you make one measurement here, it may not be that the lower crustal heat production varies on that scale, but you've got to, because you don't know that, then you have to account for the fact that it might be varying on that scale. Now that's both a good thing and a bad thing. It's a good thing because heat flow tells you about an average already. So if you want to know about lower crustal heat production, the heat flow value tells you about an average value of lower heat production over a large scale. So you don't have to go and measure lots of rock types. The bad thing, of course, is that in principle, we cannot do a very small wavelengths set of temperature profiles because of this averaging problem. One heat flow value here is not a reliable indicator of all the temperature just on this axis. It provides you only with an average thermal structure. So that's the consequences. Heat flow provides us with a very efficient natural averaging tool, very useful to studies of crustal composition. The MOHO heat flow variations are subdued because they've been averaged out. At the MOHO, of course, what happens is that you have variations of deeper lithospheric structure, say changes of the basal heat flux into the lithosphere. So that's something that varies at the depth maybe at least of 150 kilometers, because in continents the lithosphere has got to be thicker than that, at least in those areas. So this is maybe a local variation of thickness, local variation of basal heat supply. There might be also slight variations of the radioactivity of the lithospheric mantle. But the point is that, of course, these things will all be averaged out when you look at your surface heat flow because it's deep. So the MOHO heat flow cannot vary in terms of the purpose of interpreting heat flow. It doesn't vary over wavelengths about 1,000 kilometers. So this is why we can separate scales. If you look at a geological province, the variation of heat flow that you can record over 1,000 kilometer scale cannot be due to variations of the MOHO heat flow. It's got to be due to crustal structure. So early workers were hoping that at a single stroke measuring heat production and heat flow on a few selected sites, then they could get everything and strip out the radiogenic heat production signal. Unfortunately, as the number of measurements go up, this turns out to be not very good. So I'm just going to show you one example from the Trans-Hudson orogen. That's mid-Proterozoic orogen, about 1.8 billion years old. That's basically cements the slave and all the provinces to the superior province, and a smaller Archean craton called the Sask craton to the south. So that's basically the final assembly of the North American craton as we know it today. And so there's a lot of different belts. All these belts are different of different origins. Let's not worry about the geology for now. So heat flow, local heat flow, one value, local heat production. And you can see that if you're a geochemist, you can draw lines to these, but no, there's no.
That's when it's really exciting.
Yeah. Okay, so there's no relationship for the belt, and it's true for all the other areas in the Canadian Shield. You cannot get anything out of these local measurements. You've got to do something else. So you've got to work on the right scale. So the scale for a repetitive heat production model has got to account for local variations of heat production in the crust over, say, 35 or 30 kilometer thickness. We will take advantage from the fact that these are attenuated bilateral diffusion. And again, we know that they will get smoothed out. So you need to work at about this scale. So we can test this now because we have enough data. I show you these windows in the Canadian Shield. These windows are just windows that are about 200 by 200 kilometers squares. And so that's the right scale for averaging. So let's see what we've got for local measurements. You can see again that's heat flow as a function of heat production. That's a set of data taken randomly. Again, not much correlation between the two. Now we're going to go and look at windows. So 200 and 200 kilometers windows. You start to see now that there's some correlation. Even a geophysicist will draw some line in these things. And so this is the right scale. You can see also that all these things are bunched up here. And so there's basically two kinds of terrains there, and I'm not going to go into this, but you can see that already we start to see meaningful trends here. That's good because that means that this heat flow is representative of the crust, but it also means that the averaging that we've done on heat production is also telling us about the average crust.
Well, what's the scale on the local measurements?
Sorry?
What is the scale on the local measurements?
These are individual measurements. Individual measurements are taken at random. Okay. So
those are individual?
local, individual, one heat flow data, one local heat production. These are the averages that have been made over these windows, averaging all the heat flow, all the heat production. Yes? Yes. Yes, we do this systematically. When you measure heat flow, we collect the core for measurements of thermal conductivity, and then we get uranium, thorium, and potassium measurements. So we get heat production. You can't do this. In the early days, this was not done systematically, so there is where there had been a geochemist who had been keen to look at this same rock, so you had the heat production, but this was not systematic. We do this systematically. And that's why it's time-consuming. The local geological unit that your borehole goes through might be a pluton, might be a granodiorite, might be a tonalite, might be whatever.
Your natural averaging takes care of the heterogeneity.
Yes, yes.
What about the heterogeneity? You only sample a small portion.
Yes, so right now I'm not saying anything about vertical. I will go about this in a minute. I'm measuring this thing that leaves the Earth, so that's taken into account all the heat that's produced in the crust. And so the only thing I can tell you is that on that scale, what I'm seeing is a crust which is relatively now homogeneous, because it's recorded as it's related to the heat flux, so the heat flux and heat production are telling us the same thing. And it's not saying that I know what's at depth, but it's saying that over that scale, the crust is basically reflected in the heat flow. Now, if you look at even a larger scale, 500 by 500 kilometers windows, and there you might say there's not too many measurements there. There's only 5 points, but this is a lot of data because each one of these points has done a lot of averaging. You can see now that the trend is almost perfect. In fact, it's almost too good to be true. Transverse origin, Granville, Superior, Slave, Appalachians. Yes?
So I the pop figures individual measurement.
Yes.
You do the window, how you actually can get a larger heat production.
Now, these are just selected a few, because otherwise I would have a point would be, I said it's only a few measurements just for, in one particular area. It's in fact, the measurements for one of those windows, within a window. You can see there's not much there. Now, you average all these things, and you get one value here, and other things, and that's what you get. And that's, all this goes into one of those points. Okay? Now, vertical variation. Yes?
I was thinking about when you average, of course, how many samples you have in each region and how the coverage is uniform.
We've chosen the windows so that we had enough variability and so that the standard deviation was sufficiently small. So, for example, if you have low heat flow values everywhere, the main problem is the high points, the high radiogenic plutons. I'm not interested in those because I know in the areas, I've got a geological map, so they're scattered. And if I happen to have heat flow measurements on the radioactive plutons, I'm not happy, but because it's going to be reflecting this local heat production. So basically, it depends on the areas. If I don't have any sample over these plutons, then it's much better. So none of these windows, the minimum is six data points. Yes?
So the lowest diagram, is that all Pluton or all?
No, it's everything. Everything. That's the trick, is that you don't want to focus on an individual or specific rock type. We've been measuring, for example, the Appalachians. I did this a long time ago. I went and measured heat flow through a meta-symmetry series because in the Appalachians there's lots of those. If you focus on the White Mountains magma series, for example, you're focusing on a very late, highly enriched set of plutons that do not tell you much about the average crust. So we made sure that we would measure heat flow away from these specific plutons. Is that clear? Yes?
Another question, make sure I understand how this works. So, these are all samples of exposed basement. So, if you went to a place like the Western Canada Sedimentary Basin that's overlying the basement, I mean, this.
Too bad. That's the problem. Okay, heat flow I've measured several times heat flow. It's in sediment basins. It's a mess. Sediments are porous. They carry water flow. It's a problem. So, if you go very deep enough, then you might start to make sense. We've looked at all this data. There's a lot of data from the mining industry or the oil industry, borehole temperature, etc. You can make sense of the data, but it's extremely noisy. So unfortunately, and indeed, if you log a hole through the sedimentary series, you have no information about the basement and what's there, or you have scant information about that. So, in a few cases, in the Canadian Shield, just at the tip, northern tip, for example, of the Williston Basin sedimentary series, we were able to bores that would go through the sedimentary series and then into the crystalline basement. So they were happy enough to do that. But usually the ones in the sedimentary the reflow are not reliable. So how do we go about measuring the Moho heat flow? Well, first, the best way would be to have temperatures versus depths below the Moho. And this is provided us by studies of Xenolis. And so just to, sorry about the French, it's not going to be a contest. Those who can translate this will get the book. So, slave and superior. Okay. And Canada is Canada. So that's depth and temperature. And two data sets that spans a lot of. This is from Kirkland Lake in the Abitibi province, and in the Slave province, that's the Jericho. Comes from the Jericho. You can see that interestingly, there are definite lateral variations of temperature across the shield on that scale. There's about 150 or 200 degree difference between these two profiles, which is telling us something. And you can draw a gradient to this. The average gradient for these things is about 5 degrees per kilometer, and the heat flux is about 15 milliwatts per meter square. You can see, if you remember, the shallow bores I was showing you in Canada, where I've taken low heat flow bores with low gradients. The lowest gradients we measure are about 10 degrees per kilometer. You can see that now if you're in the lithophilic mantle, the gradient is definitely much lower, which means that the heat flux is definitely much lower than the one we measured at the Earth's surface. So what is the difference due to? Well, this is telling us about the heat flux that's going through the mantle into the crust, and what we've measured is the heat flux that's leaving the crust. So the difference between the two is the amount of heat that's been produced in the crust. Yes?
What is the eruption age of those kimberlites?
Now, the Jericho, I forgot, it's about 300 million years or something. And the Kirkland Lake, I don't know. I have it somewhere. They're not old. There are variations. If you look, interestingly enough, in the Slave province, I have that plot somewhere. There is a systematic, Dante Canil has done a nice study of this. If you sweep there's a set of kimberlite pipes that span in age between, I think, 500 million years and 55 million years. And if you look at all the data, there are some variations in between those two. I've looked also with David Bell at kimberlites from South Africa, and I looked at I forgot the one because I was concerned about time variation. And we looked at data, most of the data from, I forgot, from South Africa was from one of the older generation of younger generation of kimberlite pipes, and I wanted to get an older one, so we worked together and he determined the temperatures, and over about 100 million years, there's a difference of about 150 degrees also between the two geotherms that you can derive from these South African kimberlites. Now, the one we looked with David Bell, it's early morning, I'm not a morning person. But anyway, the name will come back to me. This difference in temperature, it cannot be due to, I think, a time evolution, because over that time scale, what you're looking at the equilibration temperature between minerals, and so if you change temperatures, the minerals have got to re-equilibrate, and that will be sensitive. That has to be achieved by solid-state diffusion. And for that, the scales of the grains in those rocks in 100 million years, you don't have time to re-equilibrate temperatures that efficiently. So these have got to represent spatial variations of temperature, not time variations of temperature in the lithosphere. And the same thing for the Slave, I think. Now, as I will show you later, because the heat production varies, we don't have any problems with explaining a temperature difference of about 150 degrees C between these different parts of the Equatorial Shield. That's not a problem at all. So local heat production, local crustal structure is different beneath the Slave and beneath the Abitibi. So that will generate temperature variations and over just about that kind of magnitude.
Like your previous figure, what is the significance of the y-intercept?
Well, you see that's the intercept at zero surface heat production. Now, there's no such thing as a zero production, but basically tells you that for all the North American data set, what you have here is the heat flux beneath an upper layer where the heat production is the values that we've been recording in the thing, you've got a heat flux of about 33 milliwatts per meter squared. So the intercept is basically the heat flux at the base of the enriched crystal upper layer. Okay.
I can't read all over the place of America. Is it remarkable that basal heat flux is constant?
Yes, it is remarkable. Yes. Now, remarkable here. Remember that the heat flux here. If you look at if you do a little bit of statistics on the line, the heat flux is determined to plus or minus 3 milliwatts per meter squared. So 33 plus or minus 3 is a 10% variation. That's a lot. But to that level of variation, it's constant. Yes. It means that, of course, there is some heat production in the lower crust, and that might vary by a total max of about 6 milliwatt per meter squared altogether, but that it doesn't vary by much more. Now, if you look at the various models for lower crustal heat production, it's not a problem, but that's what you find. That's indeed. This is remarkable. Most of the, and I will come back to that later on, most of the crust has got its heat-producing elements at the top. And so what's left is, you can't vary that much. There's not much left below anyway. So to make a significant impact on the heat flux, then you would need to have very large variations of these rock types. And anyway, they're quite depleted. So it takes huge amounts of variability to produce a heat flow signal there. Okay, so you can see now we measure this on the right scale, about 200 kilometers. We measure this using all sorts of tricks. And now, so we have the bulk heat production. That's not enough, because we saw from these data that the heat production is actually segregated. There's more stuff at the top than at the bottom of the crust. And to make a reliable thermal model, we need to do something about that. But the other thing we've measured is the average heat production. And I've shown you that the average heat production is indeed relevant on that scale. It is the heat production that makes the heat flux vary. So we have also the surface heat production. So because we've got the surface heat production and we've got the bulk heat production, we can have a very simple index of the vertical stratification, because we can compare the two. And that's the trick. So we can estimate the degree of enrichment in upper crusts, and that's what we call the differentiation index. It's not a very good name, but that's what it is. So that's the surface heat production, suitably measured over the right kind of scale, divided by the average. So the average is surface heat flux minus Moho heat flux divided by crustal thickness Zm. So that's why Zm eventually shows up on the numerator. And that tells you if di is equal to 1, then what you have is an homogeneous crust. What's at the surface is exactly what's below. And di is usually larger than 1. That means that the surface heat production is much larger than the average. And so the crust is vertically segregated with an enriched upper layer overlying a depleted lower layer. And that's a nice trick, very easily done. And that's the best thing we can do. But, yes?
You say that usually di is greater than 1, but are there cases where it is 1?
We've got a few cases in the Canadian Shield which is 1, yes. In particular, in the north, if you know the local geology, the North Caribou terrain, it's about 1, which is the earliest continental block in the area. We see a very marked difference between in fact, we're writing that up right now, between the core of the craton, the pre-3 gigayears crust, and the later belts that were accreted to that craton. There's a marked difference in both the heat flow and production and the differentiation index.
So it's more differentiated outside the core?
Yes, yes. Bill?
Is there also a consistency with, say, seismology that maybe a monolithic crust?
Sorry?
A monolithic crust, once, granite from top to bottom?
I'm not sure what...
From seismological data.
You mean the differentiation index or whatever?
No, when you have d equals 1.
Oh, yes. Well, in that area, there's not much North Caribou terrain, so there's not much. There are areas where d is less than 1, and in parts of the IBTB, if you've got your sampling stuff on the greenstone, large amounts of greenstone, they've basically no radioactive elements, and they sit on tonalites or granodiorites, and so there what you've got is d is actually less than 1, because your surface heat production is actually, almost zero for practical purposes, and most of the reactivity is below the greenstones. No, it would be nice. There's a bit of data through the North Caribou, and unfortunately the seismic data doesn't, for example, doesn't show much internal crustal variation. If you look at the belt toward the south, we're talking about the Superior Province. The Superior Province, for those of you who don't know, is something that's a piece of crust that got formed over at least 1 billion years. For the oldest pieces of crust that you find there, they might in fact be older than this, but reliably we've got a lot of samples from about 3.8 gigayears in one way or another, mixed in with some other components. And the big craton is made of a core, which is the North Caribou, and towards the east it has another name which I forgot. I think they call it the Hudson terrain. And then towards the south, what you have is a series of belts. There are volcanic plutonic belts, and interspersed with metasedimentary basins, best interpreted as a series of island arcs that got accreted to the craton, and with the marginal basins and maybe the accretionary complex that got squeezed in between successive island arcs. So what you have is an alternation of volcanic plutonic belts and metasedimentary belts. And we know from the seismic data that it's interesting, in fact, that the thickness over which you have the enriched metasedimentary belt is about 10 kilometers or so, which is something which we can see. In fact, if you look at this plot, the slope of that line, which gives you the thickness of that enriched layer, is, guess what, 10 kilometers. So now we've got enough, because from this data, we have reliable heat flow data on the right kind of scale. We've got the right heat production. We know we have some index for the differentiation. We have an idea over which the enriched upper crust is enriched, about 10 kilometers, and that's enough to make calculations. So what we do is that the procedure now to calculate geotherms over these windows, we have the measured surface heat flux, suitably average, enriched upper crust, measured average heat production. D, we can leave it as a variable, as I'll show you later. QM, we estimated using all sorts of means. And then we have the typically lower crust. In the Canadian Shield, we have two nice areas where it's exposed, not maybe down to the lowermost crust, but we have two in the Sashigo-Piquitone belt and the Wawa Kapuskasing belt. We have two areas where we've got very deep crustal samples that are exposed on a large scale. So we have estimates from the lower crust here. We know the crustal thickness. And of course, D might vary a little bit, and this is not very tightly constrained. We can, but the key thing is that even if it varies a little bit, given what we think about it, then the impact on the temperatures is not large. There's a large impact on temperatures if you do not assume that the crust is vertically stratified. So that if you take a homogeneous crust with the same bulk heat production, then you will get a very large impact on your temperatures. But once you take an enriched upper crust, it doesn't matter that much if it's over 8 or 10 or 12 kilometers. So there's going to be some error in your temperature estimates, but it's much reduced now. So what I'm going to go through now is a series of calculations that show you what is the impact of the various parameters now. Say I've got an area, I've got the average heat flux. If I don't know much more about it, what's going to happen? So, for example, let's steady state geotherm. Now, I'm going to carry them to the bottom of the lithosphere. Surface heat flux of 890. This is a randomly picked value. If you put all of these profiles will have a Moore heat flux, and in fact, basal heat flux of 15 milliwatts per meter squared. So this is kept constant for these two calculations. Now, from this and the Moore heat flux, you can figure out what's the bulk heat production. Now, the crust is homogeneous, or if it's stratified. You see the impact on temperatures. Here, the impact reduces because of the biggest thermal conductivity depends on temperature, and that will tend to decrease the range. But you can see at the base of the crust, right here, the slack in temperature is something like 300 degrees. So if you take a homogeneous crust or a stratified crust, you're likely to err by a large amount on your crustal temperatures. Roberta?
Just a point of clarification, it's the exact same crust composition.
It's the same bulk heat production, either homogeneously distributed or stratified in the upper 10 kilometers with some lower crust, as I've shown previously. And you can see the enormous difference in the temperature. So it's extremely important to account for vertical stratification in the crust. Now, let's vary the amount of heat production in the crust. Again, Moreau heat flux and basal heat flux are kept at the same value. Again, we have the variable upper crust. Lower crust is kept at this value, which is about the value that you get from these two big outcrops in the Canadian Shield, Peak between Echachigo and Kapuskasing. And so if you have this fixed and that fixed, then if you vary the upper crust, of course, you vary the surface heat flux. So take it reversely. We measure heat flux, 90, 65, 40. And this is, in fact, in the Canadian Shield, we don't have values as large as this, but we have, in fact, values from 65 to about 30. Okay? So I should have done the plot here, but you can see that the impact on the temperatures is still large. It's about 150 degrees C. So, of course, across the Canadian Shield, you've got heat flow variations from about 60 to about 30, variations by a factor of 2. And again, this is going to give you a total variation of temperature about 300 degrees C in the crust from one part to the other. So large variation of temperatures just due to the local heat production in the same basic craton. Now, if you vary the Moreau heat flux, the Moreau heat flux is small, so we varied it between 12 and 18. This is, I think, about the range that we can account for using what we have. Same surface heat flux. And this is, I forgot whether it's stratified or homogeneous crust. I think it's homogeneous crust here. Just to show you the impact of this number. You can see at the base of the crust, it doesn't play that much of a role, although that's quite a large variation in the Moreau heat flux, simply because in the crust, what determines temperature above all is the heat production. This is the largest by far factor that determines temperature. The Moreau heat flux kicks in, of course, as you go deeper, and these profiles will diverge because the heat flux will tell you about the gradient at the base. But as regards the crust, then it's mostly the heat production that matters. So the conclusion from all these simple calculations, they are just sample. Crustal stratification and depletion of lower crust is as important factor as change of basal heat flux, and maybe even more, and change of bulk heat production. So you need to worry about crustal stratification. That's a very important factor. So can we check this? This is fine. All these calculations, this heat flux, maybe we don't know what we're talking about. So when you don't know what you're talking about, the next thing you can do is that you talk to somebody else who doesn't know what he's talking about either. And if you somehow say the same thing, that maybe you get more confidence. So we've been talking to seismologists. And so what you have is, if you look at VP as a function of temperature, depending on composition, you've got, there's a compositional effect here. You can see that there are different models from Roberta, Rudnick, models from Griffin, Bill Griffin in Australia. So there are variations in the composition, but you can see that the effect on temperature, if you look at the crust, usually the temperature variation will overwhelm the compositional variations. But you can see that you can predict there's a very specific slope here. And so that's the one thing we can check. And we can also, in fact, compare the absolute velocity. So this is what we've done in the Canadian Shield, because there's lots of data now. So I'm going to take you to that part of the Canadian Shield around that's Hudson Bay, Abitibi. I'll tell you a little bit more later about the Kapuskasing structure, which is this funny little thing here, which is a late feature. And all these are the belts that I was talking to you about. In fact, the names have changed since then. Each time I read a new paper by the Canadian Geological Survey, they've changed the names of this belt, so it's becoming confusing. But it's called, I think, that's the North Caribou now. Anyway, these are all you can see there's a lot of variability of the structure. These are the belts I was telling you about. That's the core of the craton. English River is a metasedimentary belt. Wabigoon is a volcanic plutonic belt. The Ketiko is, again, metasedimentary, and Wawa Abitibi is a volcanic plutonic belt. And you can see the core of the craton here, and all these belts that got accreted towards the south. In that area, that's been outlined here. There's been a lot of seismic refraction, and we have lots of heat flow data. Seismic refraction provides us with PN velocities at the Moreau, and we think it's a much better value to use than what we get from global inversions of surface waves, because it's a local measurements over a reasonably small scale. It's hard to figure out exactly over which kind of scale, lateral scale, the PN velocity has been determined, but it's probably something like 100 kilometers or so. So it matches about what we have. So we've compared the PN velocity in that area with the calculated temperature. So this is what we do. That's a map of the PN velocity across that area. The dots are the measurements where the PN velocity was determined. As you see all the refraction lines that have been run. And you can see the PN velocity varies. Okay, across the color scheme is from 8 to 8.3. This is not a lot, but this is what we've got. Now this is the heat flow field over that area. Again, the dots. Sorry, again, the points from the paper. Where is that? The new data points. That's to give you an idea. To get these new data points, it's about 3 years of work. Okay, so that's exciting. And that's the heat flow variations. You can see that in that area, heat flow varies by about slightly more than a factor of 2, and you're within a rather restricted piece of old continents. So heat flow varies. So then we've done what I've shown you before. We can calculate the Moho temperature using these windows. So we've split these things in 200 by 200 kilometers windows. When there's no data, we didn't do anything, of course. But then there's enough measurements that we can compare to the PN velocity. So what we have is a map of on top PN velocity and a map of temperature. That's the observed PN. That's the calculated temperature using algerotherms. Now you can see there's obviously some kind of correlation, but we can take it further. Now we split this into these windows, averaging windows, and this is what we get. So average PN velocity as a function of Moho temperature, and this is the data points. So there's a definite slope, not great. But interestingly enough, remember one of the free variable in the calculation of the geotherm is the Moho heat flux. We've taken that value here. We'll see later what it does. And the slope of that line, the best fit line, is this, 0.6 times 3 kilometers per second per degree. And that's consistent with what is known about the temperature dependence of seismic velocity. That's one thing. So we know we're on the right track. Can we compare a little bit better? If you now introduce a model for, yes? Kelvin. So max is about, you can see it's max about 700 degrees Celsius. Max. On average, it's about 400 in that area. But this is an area where we took, of course, where there was the largest possible variation, because this is where we could get these samples. If you look at this shield on average, what you get is the Moho temperature. I'll show you later data on this, about 400 K. About Celsius. Sorry? Sorry?
Seems a little high.
Well, that's what it is. It's what you get here is temperatures that are reaching just on the threshold about 800 in this area. Base of the crust, yes. Oh yeah, base of the crust, Moho. There are thickness variations here in the Moho, so that adds to this. Yes? They are calculated from the heat flow data, the way I've done it, and I compare this to the measured PN velocity. So what you have is PN observed as a function of estimated temperature, and we should have this slope. Okay, and that's basically what we've got. Now we can do better than this.
Sorry,
Yes?
so here you are considering that your variation in velocity is equal to the variation in temperature.
Yes.
You're not taking into account composition.
Well, I'm going to go to this in a minute. Okay. So we can compare this now to a compositional model. So if we take an off-Creighton model with the off-Creighton composition, we could have taken from Roberta. We have some variations in the variations of elastic properties that we account for. That's the gray line. We've done this with Nikolai Shapiro. And this is these arrays of points. We can have different arrays, and they indicated the variable here is the Moho heat flux, so that's 0, 15, 25. You can see with that kind of composition, although the middle one is not too bad, it's not too good to fit because of the slope. The slope is just not quite right. So these kind of compositions we could rule out. Now, if we take the Crotonic composition, that's from Roberta, but we've also taken some other things, archon and protons from Griffin, and then added the slack in the elastic constants, you can see we got a much better fit in terms of the slope and the position of the geostorm. So our preferred thing is here, 15, which in fact is better fit by a proton model than an archon model, and there's something there that we could maybe work. There might be lateral variations of mantle cohesion across the area. That is something that, of course, at that kind of scale we can't vouch. But you can see that there's now quite a reasonable correspondence between the temperature that we estimate and the seismic velocity. So we're talking about the same things, with not that much of a difference between the two variables. So that gives us confidence that we're on the right track to estimate correctly crustal temperatures.
And the composition are anhydrous.
Are
Are
anhydrous,
anhydrous.
yes.
Because the water can have a big effect on the.
Well, yes, of course. We don't know the water. Well, there's a bit of data that's starting to come out on the water content of the Canadian samples, but not much from the Canadian Shield, I guess. And Peli has been doing some work, and I think she's done most of the work for South Africa, but I didn't see much. When we published this in 2006, there was not that information, just in anhydrous composition.
So just to go back to the earlier question, so are you in fact saying that locally you think there are temperatures at the base of the crust in the Canadian Shield that are as high?
In these areas, yes, yeah. And in fact, it's again, if you look for these velocity values, that's what you get. These areas of thick crust, and yeah, that was a surprise to us too. But I'll come back to that. I'll come back to that in a minute. I'll come to that. In fact, that's the next topic now. You've got, of course, when the crust is thick, even if it's depleted, then you got an increase in temperature. Okay, and so we'll see that there's areas it might be missing. In fact, sometimes it's not the thicker crust; it's complicated, and I'll show you. No, beneath the Kapuskasing uplift, you reach 55 kilometers. Generally speaking, Canada, it varies. In fact, you had the plots there. Well, I'll show you the plot with crustal thickness later. Sorry. Okay, so this is also what you see when you measure. I didn't have nice geological photographs to break the so let's talk about general global systematics. Okay. If you look at heat flux and crustal thickness, let's say you would say if I've got an average crust, the thicker the crust, the larger the heat flux, because I have more radiogenic heat production, so I should. And well, no, this is from a global database. I'm not going to draw lines to these things, but no correlation. Yeah. Now temperatures. Now we can account for local crustal variability, etc. So Moho depth, Moho temperature, and then we take into account what we think we know about crustal variability on average. And now we start to see some correlation. So that is to say that indeed you cannot use heat flux to estimate things very accurately because heat flux is going to be sensitive to crustal heat production, and crustal heat production varies. If you start accounting for crustal heat production, then you can get temperatures and you can make sense of the data. So crustal thickness is not a reliable indicator of heat flux, and heat flux is not a reliable indicator of crustal thickness. Roberta?
Just to clarify, this is a global data set?
That's a global data set. We calculated the Moho temperatures using the models we had and assigning for each areas the Archean crust or Proterozoic crust or whatever. So there's going to be some local slack and the Moho depth from the crust 2.0.
Where are those areas that are 800 to 955?
I'd have to look at it carefully. I didn't look at it carefully. We have a few of those in the Canadian Shield that I can tell you about, and I will come back to that later. But this, I don't know. We didn't look at all we run through a big code, and we should, but that's yes, I'll come back to that in a minute. Yeah, of course. Yeah. You're reaching. It's not to say these are accurate. We've just run in those areas. We don't always have the right. I'm not saying these are correct temperatures. What I'm saying is that when we start to input some crustal information on the heat flux and calculate temperature, we start having make sense. But you can see that the slack is still very large. And so each one of these data points is probably accurate to only a few hundred degrees C because we don't have the proper crustal model. The only thing, I'm just comparing these two correlations. That's the main point. If you look blindly at crustal thickness, then it shows that you don't have the same crustal composition everywhere. It's not reflected in the heat flow. If you start differentiating between Archean crust and younger crust, that's a very rough, then you start to see some correlation. Okay? But this is not to say these are accurate. I've shown you before that within a single Canadian Shield area, if you have to account precisely for the local crustal composition, which varies, and this is just a global running through just 3 types of crust: Archean, Proterozoic, young. So very rough, but then you start to see something happening. Yes?
Did you correct for pressure velocities?
The Moho depth is from the crust 2.0, so I just get the... That's all. That's all I need. So crustal thickness variations. Let's go back to the Canadian Shield, and I'm going to show you a plot of crustal thickness. Again, where I'm going to focus is the capillary casting structure, a very interesting structure, which has, in fact, a deep root, about 55 kilometers. Now, Becky rightly said, well, if you have a thick crust, it's got to flow. Well, not always. Okay, that's the crustal thickness map. Remember, we had all these data points with crustal, with refraction lines, etc. That's the capillary casting. Capillary casting is about 50 here, 50-something. And there's areas, in fact, where the crust is actually thicker. So that's the crustal thickness map in the area. You can see that even in this part of the Canadian Shield, how the crust thickness varies. Sorry? So this point is not. It's just at the edge here. There was some refraction. I'm not sure what this data point is. In fact, no. It's. I'll show you the heat flow map. In fact.
I mean, there's one datum with a red aerial around it.
There's heat flow data. There would be lots of measurements in the Superior Lake, and I will show you that later.
What are those white dots? Sorry,
These are refraction lines, the bottom points where the PN velocity was determined. Now, that's the heat flow map. And you will see some very important things when I compare them. That's the capillary casting structure, and this is where we've got the thick crust heat flow. It varies. Okay. Again, you see in this area, it varies by a factor of 2, from about, well, say 25 to about 60. So lots of variability in the heat flux, although it's a province that's... Now, the capillary casting structure is interesting. What we have is this crustal root. There's another root elsewhere, but that's a map, rough, which you have the Abitibi, the Wawa belts, same plutonic belts, and there was some thrusting about 1.8 billion years ago, which brought up lower crustal rocks at the surface. It's a density anomaly. It's thick crust here. The crust is thick, which is not indicated here. Well, you can start to see here, but in fact it's larger than this because it's 255 in areas. So what you have, how come we can sustain a thick crust? Compare again the crustal thickness with the heat flux. You can see capillary casting is thick, low heat flow. High heat flow, high crustal thickness again, low heat flow values. What does it mean? Well, I think it makes sense because low heat flux means you have low temperatures, you don't have viscous relaxation. So if you've got some topography of the Moho, it's going to relax in a time which you can estimate roughly as this. That's viscosity. The delta rho is the density contrast between crust and mantle, G gravity, and lambda the scale of your crustal root. And so this should be fast if temperatures are high enough in that part of the world. And obviously, the capillary casting crustal root has been there for about 2 billion years, and it's unless it was 2,000 kilometers thick when it got formed, it hasn't relaxed much. So the answer is that for this to be slow, geologically speaking, then you need low temperatures, and this is exactly what we see. Those areas of thick crust are areas of low heat flow, and we see this elsewhere. We see this in the Trans-Hudson. We see this also in parts of the Grenville Front where the crust has been thicker. It's always where the crust is thickest. This is where we've got the lowest heat flow values. So again, this is showing you that crustal thickness is not a good proxy for heat flux. The heat flux doesn't tell you about the crustal thickness. It tells you about the local heat production. Yes?
Okay, I'm just trying to think my way through this correlation that you see between crustal thickness
Yes?
The fact that you see a positive correlation suggests that, and there's no correlation with surface heat flow, so it's not total crustal radioactivity, but it would be crustal differentiation, and there's more heat production in the lower crust.
It means that with those models, when you have indeed, we have the same crustal model I was showing you, if you got a thicker crust, then you've got slightly more heat production in the crust. And that produces slightly larger temperatures. We start to see correlations. But again, these are just rough models to show you that heat flux and crustal thickness do not match. Heat flux and the temperatures start to match if you account for the heat production. Okay, some global systematics. North America, just to show, can we make sense of this? Well, this is giving you this province where we have lots of data. Again, there's not a lot of areas, but that's the best we can do. Superior, Trans-Hudson, Granville, Appalachians. That's the surface heat production. That's globally average. Each one of these dots is about, there's more than 100 measurements apiece. And you see this, of course, what we all know, Appalachians crust is enriched in radioactive elements. Now, the bulk heat production from the surface heat flow data varies also. It's different from the surface, but it varies, the same kind of trend. And you've got some slack depending on the value of the Moore heat flux, but it's the same kind of trend. You've got much higher radioactivity in the Appalachians. Now, of course, the Appalachians is young. So, yes, Becky?
I was going to say, but so earlier, you showed the slave.
Yes? The slave there's not enough data point to show that. I show the slave because in fact, the slave is right here. But there's five heat flow data points in the slave. I can't calculate the bulk heat production in the slave reliably. I have five points. But it's somewhere, in fact, it fits there. But the slave would be, the slave would be here. Yeah. It's the oldest.
It's surprising to me that the Grenville is so low. It's like the Superior value.
Yes?
Yet the Grenville is loaded with granites, many which have higher radiative.
There's a few granites, but not that much. If you look at the different belts, the pyrotonous and the allochthonous belts, that's exactly what we've got. We have lots of samples from this. There's a few plutons, but there's also a lot in the Grenville. There's a lot of anorthosites. In fact, there's a lot of anorthosites over the Grenville.
Volume-wise, northosite is not a dominant rock type. Granitoids are the dominant rock type.
Not over the Grenville. If you look at a map of the Grenville, you've got lots of anorthosites on the surface. I could show you a map. I'll bring it to you. There's a lot of anorthosites.
I don't believe that.
Well, it's a geological map. I'll show you.
I can show you a map. Northosites are a minor cloud.
Not in the Grenville. Okay. I've got a map for Martin Yoll in Canada who's been spending all his life, and there's another guy who's been measuring gravity anomalies. Anyway, these are, we have lots of data, including the radioactive plutons. Interestingly enough, we can calculate this differentiation index. So that's bulk heat production now, and differentiation index. You can see nice trends that when there's lots of radioactivity, the crust is highly differentiated. And that, I think, will make sense, because then you need, if all this radioactivity was homogeneously distributed, the Appalachian crust would melt, even today. So it's highly differentiated, much more than the others. You can see that these older belts are not highly differentiated. But if you focus on that area, there's some relationship too. Okay, so there's a relationship between the differentiation index and bulk heat production. That, I think, is telling us that there's an internal control on crustal structure. Simply, the radioactive elements, the crust just adjusts its heat-producing elements to ensure that it's thermally stable. If there's a lot of heat production, then it's segregated some at the top to ensure that it doesn't melt. If there's less, then there's maybe less of a thermal stratification. Now, we can also go back in time. And now heat production, of course, goes up as you go back in time because heat-producing elements decay. So that's heat production scaled to the production today. So we start at 1, and as we go back in time, heat production goes up. Remember, this is a lumped effect of all the radiogenic isotopes. Thorium has a half-life of 14 billion years, 14, so thorium doesn't change much. But uranium-235 and uranium-238 have got much shorter half-lives, and so this is why this curve goes up. And if you go back in the Archean, say about 2.7, the heat production is about 2.2, 2.3 larger than it was today. So let's correct for the bulk heat production that we saw for these various areas as a function of age now. That's the corrected bulk heat production at the time of stabilization. Appalachians, Granville, THO superior. There's some slack here in the data. And you can see now that all these data points are basically the same values. There's not much variability left anymore. So what this is telling us, I think, is that these crusts, basically somehow, they're quite different, but they almost make sure that they've got the same kind of thermal structure. Yes?
Well, given this, it's surprising that they have a different differentiation.
Well, there's still some differences here, okay? And there's still you can see it's about yes. There's maybe an erosion problem here. I'm just calculating things as they are. So that's what but you can see that essentially the main I think important message that the Appalachians, which are really far off, is now not that anomalous. There are some variability there, and certainly the superior province requires a bit of study, because depending on whether you look at the western side or the eastern side, there's some variability. For example, the western IBTB is not exactly the same as the eastern IBTB, so global systematics are only valid in so far as they give you bulk ideas, but then there's something. Here you've got about 30% variability, which is quite big. Bill? The slave would be off scale, yeah.
Is that why you say the data points really?
Well, I had it put in initially, and it's right there, and there's not much to say except that I have so few heatful data that I'm not sure that what I get. I know that the surface rocks are highly radiogenic. There's no doubt about that. We did make a few measurements there. In fact, we had a paper with Andy Nightblade several years ago on this. We had some data from mines, etc. So I think there's about 3 or 4, maybe 5 max heatful data points. So I'm not going to put my head on the block for 5 points. No, it is anomalous if you just take the data for granted. It should show up here, and so. Sorry. The Wapme is Proterozoic. The Wapme. Should I say this way? Well, if you look at the paper, there was a paper by Lewis and Heidman, and they have some radioactivity. If you read the paper carefully, you see that they've corrected their crustal radioactivity by a factor of about 2, because for some unknown reason. So they have a higher heat production than what they actually measured for. And I can't understand now why they do such a wide correction. So Wapme is high heat flux, high heat production, yes. But the heat flux data, most of the heat flux data are in fact sedimentary basin boreholes, no conductivity measurements. They're estimated, so I'm not comfortable with that.
Well, what do you make of the fact that these 4 provinces of very different ages have roughly the same heat productivity?
I think it's because somehow by the time you stabilize and maybe you've eroded that, they have to reach the same kind of thermal structure. That's what this is telling me. That is, they have somewhat. Some erosion has been going on. They segregated their high radiogenic heat plutons, and so basically what you're trying to do is get the same kind of thermal state. And I would, yes?
So what are the average excavation depths of the basement like? I would think these old guys, they seem deeper.
No, well, the superior, it's variable. In fact, there's most of the plutonic belts in the superior have got almost... They've got buried beneath sediments. Becky told us about this. But by and large, if you go to the superior, you've got these lava flows. They look fresh, like they've been erupted yesterday at the surface. So the basement has not been eroded very deep. So the basement is just about the same. The metasedimentary belts show higher metamorphic grade. So let's say the Ketico, if you remember this metasedimentary belt that was lying between the Wabigoon and the Wawa plutonic belts. This shows, I think, amphibolite to granulate facies rock, so that has been highly eroded. Trans-Hudson is variable. In fact, there's the Thomson belt that has some nice variation in metamorphic grade. Grenville, it's also varied. Grenville is a bunch of terrains that both were allochthonous and some which were autochthonous, so it's a mixture of things. So yeah, again, global systematics, just to show you, the point here is that I don't want you to focus on I've shown you in the superprovince that you've got to account for local things, so I'm not going to go back from that message. It's just, when you look at all these pieces of crust, in fact, they're not that dissimilar. That's the main point. If you have to correct for age, you have to worry about that. Then the Appalachians, which look completely off scale, is not off scale anymore. That's the main message here. Let's say the slave, for example. The slave is anomalous, so I've taken this plot because it shows, of course, there's a lot of crustal radioactivity. If what we know about the slave is correct, this is what you would see. Present day geotherm through the slave. Temperature is a function of depth. Now correct this to 2.5 because there's been some plutonic activity which saw the final amalgamation of the slave against docking against the rest of the superior province, etc. And 2.5 GeV, there was some plutonic activity then. Then that's, let's say, at the time destabilized because that's the last trace of this activity. If you took undifferentiated crust, all the radioactive elements that we think are there because with this meager heat flow data set, you can see these temperatures are way off. So 40 kilometers thick, then you're above 900 degrees C. That should melt. Now you differentiate the crust, you're back to, even this highly radiogenic crust, you're back to something like 650 or something. So this is to say that undifferentiated crust is not thermally stable. Differentiated crust is thermally stable. And I think what's interesting is that these last batches of granites that show up in all these provinces, they're atectonic. All the deformation goes on. You got metamorphism in it. And then you see all these granites popping up. And that's the last thing you see in these provinces. That's true for the slave. That's true also for the superior. And so what I think is happening is that you form the crust. Then this crust is poorly differentiated because it's been stuck like that. And then it heats up with its own radioactive elements. And it's not stable because it's poorly differentiated. So what you have is that the lower crust starts melting, and then all the radioactive plutons segregate to the top, and that's it. Your crust has been made stable.
But Claude, what I remember from Superior and whatnot was that your differentiation indexes were not much different from 1.
In the superior province, depending on that's a global value, that's the problem with the local systematics. If you look, for example, at the superior province in the Abitibi, it's even less than 1,
right,
because you got greenstone. So yeah. But
the point is that I guess that there are pieces of crust in the Superior that are not very differentiated.
no. Yeah.
And if you look at your heat production at the time that the crust formed, it is still the same as the Appalachians.
Yeah. Well, yeah, again, that's the problem with the global systematics. I could show you the same. I didn't want to do this on the super province. We can do for each and every belt, we can do the same analysis, and there's variability there. I didn't want to go into this because that would have been taking too much time, but we can talk about that. We can do this for each and every belt. If we take the western Abitibi, which is high heat flux, that's the western Abitibi. Again, this is where you've got the largest concentration of granodiorites and tonalites. And that's, by the way, seen by the heat flow and the seismic people. So, although we saw this first before, anyway. But anyway, so temperature, Moho, as a function of Moho heat flux, because that's the one thing we don't know. We still need to work on constraint. Again, in Kelvin, so strip out 273. And that's calculated for the Archean. Now, so Western Abitibi, that's the largest heat flux in the Abitibi province. Eastern Abitibi is much lower. You can see that in these areas, you would produce temperature in, say, in the 900 degrees C range. So you would, in the Archean, undifferentiated crust would certainly have melted. It's still enriched. Now that's the model with an enriched crust, and it's still marginally probably stable. At this time, we can see that the crust was probably just near melting point or had finished melting maybe. If it was not enriched upper crust, if it had been undifferentiated, the temperature would have been way up there by about 200 degrees C. So you can see the Abitibi crust as we see today in the western is just at the point where it was probably just marginally stable, with the more heat flux was just near melting point, maybe just below it. Yeah. So I'm wrapping up. Conclusion. I've got 8 plus 5. Remember, I started 5 minutes late. Conclusion, crustal certification, a necessary condition for crustal stability. And I think the message is clear from the geological record. The last thing that you see in all these pieces of crust is this granites popping up. And I think that's the crust just reacting. We've generated it. We've put some radioactive elements in it. It's not happy thermally. It melts, and it puts all the radioactive elements at the top. Other basic things about strengths. We were talking about strength. Does it matter, these crustal profiles, these temperatures? So here I've taken, again, these are global things. So if we want to go into the details, that's a problem. Total strength in teranewtons per meter. Teranewtons is 10 to the 12 newtons per meter. As a function of local heat production, what happens here is that I've taken the more heat flux at the same value. And so what you're looking at as pieces of crust that have got the one thickness of 40 kilometers, and I calculate temperature as a function of the local heat production. Of course, that's if the production varies, heat flux will vary. And for different thicknesses of crust, you can see, of course, that the strengths, if you've got no heat production in the crust, very strong, and this heat production there very weak. Now, this is about the variability that we have on the scale of the Canadian Shield. You can see that different bits of the Canadian Shield would have very different strengths. So this is to say that changes in the crustal heat production imply changes in temperature, imply large changes of strength. So when sometimes we're worried about weakening, etc., you can talk about water, etc., but think about temperatures. You've got belts, and belts are enriched in radioactive elements, some of them are, and these enriched belts will be weak because they're hotter, because they've got more radioactive elements. Total strength of lithosphere, again, teranewtons, as a function of differentiation index. Forget about all these different plots. I should have just shown this thing. It also matters whether the crust is differentiated or not. Look about this thing here. It goes from 40 when it's homogeneous, one is undifferentiated crust, to about 70. Okay. So a variation of strength by a factor of 2 just by differentiating the crust. Lastly, that's a nice brown fox. Okay. What about the Earth's mantle? So I've been telling you all this, and I think the next thing we want to worry about, does this matter? All these crustal studies might be just for local geologists or petrologists who are working about plutons. No, this is important also for the way the Earth is cooling down. Remember, the Earth is not doing a Rayleigh-Bénard convection as we know it. That's a Rayleigh-Bénard plot of temperature as a function of depth. 0 at the surface, 1 at the bottom, 2 boundary layers. So this is the boundary layer that would fit plumes, blah, blah, blah. Let's say that we forget about these plumes for a minute, and let's compare what happens in the planet as a function of heat-producing elements. So let's say we have an internally heated planet. This is what the temperature profile would look in a planet that's solely internally heated by its radioactive elements. That's the temperature profile for Rayleigh number of 310 to the 6th. Don't worry about the actual value. What matters is that what you've got is this upper boundary layer where you've got this big temperature difference, and your mantle would be at this temperature. So in a convecting system, the convecting system adjusts its temperature structure to evacuate the heat that's produced. This is a steady-state calculation, and so the Earth's mantle would be at this dimensionless temperature. I'll give you numbers later on of this, and this is the temperature of the interior of the Earth that would be required to evacuate the heat that's produced locally. Now, the interesting thing is that we can compare this with what would be the temperature of the interior of the Earth if all the radioactive elements were in the crust. In other words, what is the most efficient way to cool a planet? Is it to produce a radiogenic crust, or is it to do a very active mantle convection? And the answer is, you just put every radioactive element in the crust, and then you're done. So cooling through formation of controlled crust, primitive mantle, then you put the crust, depleted mantle, enriched crust, and that's a much more efficient mechanism. And we can scale this because I can compare it. The best way to do this is let's take 2 different planets, one in which all the radioactive elements are in the crust, and another planet where all the radioactive elements are driving mantle convection. So the total amount of heat is the same in both. That would be H conduction in a crust of thickness dc, H convection over a convecting mantle of thickness H. Remember, that would be the temperature difference across a convecting mantle. If you had, it would be a crust, it would be the same. It would be a crustal thing, and then there would be nothing left behind. Now we can scale this. Delta T convection is, there's a bunch of parameters there. That's a constant. That's your heat production. H is thickness of the mantle, thermal conductivity, thermal diffusivity, viscosity, density, gravity, coefficient of thermal expansion. That's one of the scaling laws you've been subjected to over the, I think, the last weeks or so. And that's the same for conduction. That's the conduction, heat production. Remember the same amount. DC is thickness of the crust, lambda thermal diffusivity. We can scale these two. And a dimensionless number shows up. Wow. So dimensionless number, delta T conduction over delta T convection. You can rewrite this as a function of this thing. That's a constant. DC is crustal thickness. H is thickness of the mantle, and that's a Rayleigh number. Okay. You can see, of course, that the viscosity here shows up, but at the power 1/4. And it turns out that if you plug in numbers, then this is much less than 1. So the answer is that to cool a planet, you put all your radioactive elements at the top. And that's what the planet is trying to do. It obviously is not very efficient yet, but that's definitely what it's trying to do. It's a much more efficient way of cooling a planet. Now you can change viscosity. It would require viscosity that's 4 orders of magnitude less than the one we've had today for this number to be starting getting 1. So we're really clearly for the planets that we know, the silicate planets that we know with the silicate mantles that we know, and these things are much more efficiently cooled by forming a crust than by convecting. So I've reached my conclusion in the last 2 minutes. Conclusions. Knowledge and understanding of the Earth's continental heat flow have improved over the last 30 years. And it always saddens me that we do all this work and then people still refer to these isotherms that were produced 30 years ago. So it's offensive. Okay. There are large lateral variations of crustal structure and heat production, even in a single geological province. So generic crustal models, you have to be aware of them. Even the Superior province is a mixed bunch. So that's a sad message. If you're in geophysics, you want to forget about geology. If you do heat flow, you can't forget about geology. The geology matters a lot. Poor correlation between crustal thickness, surface heat flow, and molar temperature. You've got to worry about all these things. You can't make assumptions about crustal heat production. You've got to look at it. Even an Archean crust can be quite variable. So there's no such thing as a single valid, universally valid Archean crustal model. There are marked differences between an enriched upper crust, not everywhere, and a depleted lower crust. Undifferentiated crust with the parameters that we know is usually not thermally stable. So crustal differentiation is important. The data suggests that internal differentiation in continental crust is due at least in part to internal processes. You don't need plumes, you don't need funky things to differentiate the crust. The crust is able to do it on its own. You just form it. It has enough radioactive elements to undergo melting on its own. And the last thing that I was mentioning about the mantle is that crustal growth and differentiation are key processes in the Earth's thermal structure. It's not only a problem of local geology, it's a problem of working out how the crust is cooling down. So 2 key principles for the Earth, how the Earth is working. Segregate your heat-producing elements at the top of the mantle in the crust. That's a very efficient way of cooling the planet. Segregate your heat-producing elements at the top of the crust to achieve thermal equilibrium. So you guess that the answer of all this is that you must put radiogenic production at the top of the list. This is an extremely important parameter, and that's frequently glossed over. And I'll leave you with a message of a heat flow person hard at work. Okay. Thank you.
You mentioned very early that quartz has a very different, or has a big effect on thermal conductivity. I'm going to assume that it's probably a very good insulator, so it's a poor conductor.
No, it's a high conductor. It's the highest.
It's a high conductor.
High conductor, yeah.
Okay.
It's the most conductive mineral that we know.
Oh, okay. Very interesting. Interesting for
Plagioclase is about 2.
the group
What's
worrying about quartz in the lower crust, perhaps.
In fact, we measured in the Transcontinental belt. We thought we had the Nobel Prize because we found in this Archean, Proterozoic belt, we found a heat flow of 90. So fantastic. And then we looked at the structure. It was a big quartzite layer that had been upturned vertical. And so we had just measured the heat flux through this nice vertical conductor. So it was sucking up all the heat. And so quartzite had this enormous thermal conductivity. So we didn't get the Nobel Prize.
Claude, I want to reflect back on some of the conversations that we've had earlier this week and last week, particularly
in the private conversations.
No, the larger ones. Particularly the crustal growth curves. You're talking about the efficiency of releasing heat through formation of crust, or at least cooling the planet down. Do you want to speculate on 2 things? One would be the secular evolution in the delta T conduction over delta T convection, and also crustal growth curves. Do you think for the efficiency of cooling the planet down, we would have grown crust instantly in a Fife-like concept?
Well, no, because I think, I'm working on this, so it's still early stage of the models. If you do this earlier in the Archean times, your delta T, as I was showing you there, you put this in the crust, then you would have melting in the crust. So you would not produce a stable system. Okay, so you've got 2 things. You've got to wait, I think, until... So I think there's a nice feedback there. I'm not sure how it works exactly. But if you, very early in the Earth, you're trying to form a lot of crust, which I think is what you're trying to do, you're not going to go very far because this is very weak crust. You're still going to have a lot of radioactivity there because it's early times. And so this is going to be still very hot. So it's still going to be very deforming. So I think what is the 2 things that are happening, I think you're trying to do that. You store your radioactive elements. That's a very efficient way. If you do that too early, then, okay, it's still too hot, so it's deformed, and it's not stable in many various ways. So then as time winds down, I think you're getting towards stable and more and more stable things. And this is what the story is.
I didn't see any drilling equipment in your slides. Could I assume that you use pre-existing wells?
Yes.
I see. How do you locate these wells in the wilderness?
How do you locate them? Well, sometimes you don't locate them. That's the problem. Sometimes we spent 2 days and never found the hole that we were supposed to find. We use holes of opportunity. We need coring. That's the problem. And you need more than 1,000 feet. Otherwise, you just can't measure heat flow reliably. So 1,000 footer, fully cored. It's, well, if you could get a price effect, etc., it's something like $100,000. And my grants, I can't get funding for heat flow work anyway. So I've got 0. This is what's left over from my other grants. So the total money that I spent on my heat flow work is maybe $10,000 a year. So it would get me maybe a 10-meter deep hole. So I can't do anything with this. So the way we locate, mining companies are bizarre. In Canada they get incentives for drilling. So the more drilling they get, the less tax they pay. Including, they drill holes where they can't find anything. But that's fine for us. So basically, we've got a nice relationship with them. We give them the data; it's free, and then they give us the boreholes. But it takes time. That's why it's time-consuming. You've got to talk to the mining companies. You've got to show that you pay your respects because you. And to show that they're useful to them, and they are, because before they can develop a mine, they need to know the underground temperature, because they're going to need to work out the air conditioning, blah, blah, blah. The other things we can tell them is whether the fractures are active or not. And so I didn't tell you this, but basically 1 out of 10 heat flow measurements is no good. We got a big fracture, and so water is just streaming past us. So that's information for them, because they can't tell whether the fracture is active or not just simply by looking at the core. But if we've got a huge temperature signal there, it means that the water is going through, is gushing through. So that's the other thing. Sometimes we tell them things that they don't want to hear, because We found some, for example, in one area called Flin Flon, we found this big anomaly somewhere in the hole. So it was outside we're not sure exactly what the claims were, but anyway, so we went back to the and said, we think there's a mining gallery nearby, because that's the only explanation, and we've never been able to measure holes in that area anymore. So I think there was something fishy about the mining galleries there. But anyway, so we would tell them lots, and that's why they gave us their boreholes.
I was curious if you suggest that undifferentiated crust is not thermally stable, how your results would pertain to a stable lid regime on another planet in terms of a widespread mafic crust. You would predict then that it wouldn't survive long, or? If it's mafic crust,
the mafic crust has no radioactive elements because basalts are devoid of any radioactive elements. So mafic crust is not a problem. It's the felsic crust that's a problem. The big felsic. If you look today, for example, if I look today, depending on your model for the total heat production of the Earth, you've got, let's say, between 20 and 16 terawatts, okay, for heat production in the Earth. What we know are stored in the continents, and that's a number that's better constrained, in fact, than the total number. The total number will have to wait for the geoneutrinos. Now, Bill is gone, but geoneutrinos are obviously the fantastic thing. So if you take 7, and now you have you account for the fact that you've got 40% of the Earth's surface is continental crust. You put continental crust over the whole surface of the Earth, you've got all your radioactive elements in continental crust. So right now what we have is just the right kind of crust to put all the radioactive elements away from the mantle. We haven't been, I think, able to achieve contents that are stable enough, and I think that's maybe where the answer is in this problem.
Yeah, I guess the word undifferentiated was a little confusing. When you say undifferentiated, I thought you meant mafic.
No, I'm sorry. That's why differentiation. For me, differentiations mean difference. It's not igneous differentiation the same way you would call that. So it's segregating an upper crust. Sorry about that.
So it seems like you're arguing that the cratons have essentially cooled slightly since they formed in order to sort of make them, to stabilize them. But that would predict that you would have subsidence and deposition at the surface. But a basic observation that we see in cratons is that they're actually eroded to maybe 10 kilometers depth, which would be consistent actually with warming since they formed, and that erosion probably happened pretty early after the stabilization occurs. So I'm just wondering how you reconcile that.
Well, there's two things. First, there's no doubt that they've cooled down. The crust is there, and it's not been modified, and it's the one thing that we know about crustal radioactivity is that it decays with time, and that's the major driver for crustal temperatures. There's no way you can avoid the fact that radioactivity decreases. Now, the second thing is that to subsidence, of course, you have subsidence with respect to what? With respect to an ocean basin. So you need to know also what the mantle temperature is. So there are, in fact, you can show in some cases that indeed the Earth's lithosphere might have been slightly hotter than the surrounding mantle in the past. And so there's more slack. You have two different systems that behave in different ways. You've got the Earth's convecting mantle and you've got the Earth's lithosphere. They're both cooling down. Okay. And so they're both cooling down, but not at the same rate. So it can be quite a complicated story. You have to compare the two. It's not only constants in the surrounding mantle that's happy with the same surface, and I'm not talking about the water budget, but I think subsidence is a...
Claude, did you just say the lithosphere was hotter? Because there's this evidence from diamonds. So if diamonds are Archean, that means the lower parts of the lithospheric mantle had to be pretty close to the same temperature they are today, a cratonic mantle. In which case it could address Becky's question, because then it means the cratonic lithosphere was the same temperature profile more or less as it is today when the background mantle was a lot hotter. So the continents were sinking rather, and have been floating through time.
Well, again, I would caution you again, calculating temperature and then assuming it's floating or sinking, you have the cooling mantle next door. So you have to, whether the continent is sinking with respect to the mantle, which is also cooling down. Okay, so that's one thing. Second thing is that I know about this diamond. The only thing I can tell you, I haven't done lots of these models, but the continental lithosphere has got, if it's 200 and 250 kilometers, it's basically has a time, characteristics time constant, which is about 1.5 gigayears. So for this thing to equilibrate thermally, it takes about 1.5 gigayears. So you might put a lot of radioactive elements at the top of this thing, and for about 1.5 gigayears, the bottom of the Earth's lithosphere is not going to know that it's got very radiogenic crust at the top. Now, we've produced models for this. I'll show you the papers. The nice thing that happens is that, of course, as your lithosphere is trying to equilibrate, of course, your radioactive elements are decaying. So you've got your lithosphere trying to get hotter, but at the same time, your heat-producing elements are getting colder. So, in fact, it's a losing race. And so what you have is temperatures in the lithosphere which do not vary that much with respect to time. But they might be slightly hotter or might be slightly colder in the past. This is a strong buffer for temperatures. Is this clear?
Yeah, no, I understand.
Yeah.
I guess the point being is that the relative temperatures between lithosphere and convecting mantle may change more than the lithosphere may have been cooler relative to the convecting mantle in the past than it is today.
No, I know, but you've got to start. How do you form the initial lithosphere? I think it's very different if you form the lithosphere, for example, say by hot plume. So you start with a hot lithosphere. I think this is not consistent with the observations.
I guess, Rick, can I actually comment on this a little bit? It looks to me actually is if you think the convective mantle will cool faster than the cratonic lithosphere, so let's say for the last 2 billion years, and then that actually will explain why the continents actually will kind of erode more, right? Because the mantle cools so much, and relatively speaking, the cratonic lithosphere actually will kind of keep rising, so you keep eroding things, right? So that I think it actually makes perfect sense. Everything, yeah.
Yeah, these are two systems that evolved in slightly different ways. Huh? You gotta look at it. It's not a cooling lithosphere or heating lithosphere within a isothermal and thermo-steady-state mantle. The mantle is changing temperatures also. I think all these models, the observations are. I can have various scenarios. Again, it's important to know when the continental lithosphere was formed. If it was formed hot, we've got a big problem. If it was formed cold, I have no problem. So we published a paper saying this. It's from the observations. Because then, if you have a cold lithosphere, then you put hot crust on top. Then that's the scenario I was explaining.
One of the models for forming cratonic lithosphere is in an island arc setting. So it's the wedge in an island arc setting. So it would form.
Yeah, that's what we said in that paper. Yeah. A very nice paper.
Any more questions? Let's break for coffee. It's like